Okay? The word regression simply means real valued output. There is absolutely no other connotation to it. It's a glorified way of saying my output is real valued. And it comes from earlier work in statistics, and there is so much work on it that people could not get rid of that term, and it is now the standard term. Whenever you have a real valued function, you call it a regression problem. Okay? So that's with that out of the way. Now, linear regression is used incredibly often in statistics and economics. Every time you say, okay, are these variables related to that variable? The first thing that comes to mind is linear regression. So let me give you an example. Let's say that you would like to relate your performance in different types of courses to your future earnings. Okay? So this is what you do. You look at, here are the courses I took. Here are the math, science, engineering, humanities, physical education, other. And you get your GPA in each of them. So here I got 3.5, here I got 3.8, here I got 3.2, here I got 2.8, 2.8. No, that doesn't happen at Caltech. Okay, so you go for the other one. So you just have the GPAs for the different groups of courses. Okay? Now, you say, okay, someone graduates, I'm going to look 10 years after graduation and see their annual income. Okay? So the input are the GPAs in the courses at the time they graduated. The output is how much money they make per year 10 years away from graduation. Now you ask yourself, how do these things affect the output? So apply linear regression, as you will see it in detail. And you finally find, oh, okay, maybe the math and sciences are more important. Or maybe all of that's an illusion. It was actually the humanities that are important. You don't know. You will see the data, and the data will tell you what affects what. Okay? And any other situation like that, people simply resort to linear regression. Okay, so in order to build it up, we are going to use the credit example again in order to be able to contrast it with the classification problem we have seen before. So what do we have? We have in the classification, we have the credit approval, yes or no. That's a classification function, binary function, which say the output is plus or minus 1. In the case of regression, we will have real valued function, and the interpretation in this case is that you are trying to predict the proper credit line for a customer. So the customer applied, and it's not a question of approving the credit or not. Do you give them credit limit of $800 or $1,200 or $30,000 or what? Depending on their input. Okay? So this is a real valued function, and we are going to apply regression. Okay. Now you take the input. This is the same input as we had before, data from the applicant that are related to the credit behavior. So the age, the salary. I suspect that the salary will figure very significantly now when you are trying to tell the credit line, okay? Because if someone is making, $30,000 a year, you probably are not going to give them a credit line of $200,000, okay? So you can see that this will probably be affected. Okay, and there are other guys that merely have to do with the stability of the person. Years in residence, if the person has been in the same residence for 10 years, they are unlikely to skip town. On the other hand, if they have been there for only 1 month, well, you don't know, that type of thing. So you have these variables, you encode them as the input x, and then your output in this case, which is the linear regression output, is a hypothesis form, which takes this particular form. So let's spend some time with it to understand it. First, it's regression because the output is real. It's linear regression because the form in terms of the input is linear. Okay? Now, we have seen this before. We sum up from basically 1 to d. These are the genuine inputs, the weighted version of the input variables. Okay? And then we add the mandatory x0, which is 1, which takes care of the threshold, which is w0. So this is the form we have seen before, except that when we saw it before, we took this as a signal that we only care about its sign. If it's plus, we approve credit. If it's minus, we don't approve credit. And we treated it as a credit score per se, okay, when you take out the threshold. Okay. Now, in this case, this is the output. We don't threshold it. We don't say it's plus 1 or minus 1. There is W0 in, but we don't take it as plus 1 or minus 1. We take it as a real number. And this is the amount of the dollar amount we are going to give you as a credit line. Okay? Now, the signal here will play a very important role in all the linear algorithms. This is what makes the algorithm linear. Okay? And whether you leave it alone, as in linear regression, you take a hard threshold, as in classification, or as we will see later, you can take a soft threshold and you get a probability and all of that. All of these are considered linear model. And the algorithm depends on this particular part, which is the signal being linear. We also took the trouble to put it in vector form, and the vector form will simplify the calculus that we do in this lecture in order to derive the linear regression algorithm. But you can always, if you hate the vector form, you can always go back to this. There is nothing mysterious about this. This simply has a bunch of parameters, W0, W1 up to WD. And if I'm trying to minimize something, you can minimize it with respect to scalar variables, which applies very primitive calculus. Okay, but we obviously will do it in the sort of the shorthand version, which is the vector one or the matrix form, in order to be able to get the derivation in an easier way. Okay, so that's the problem. What is the data set in this case? Well, it's historical data, but it's a different set of historical data. The credit line is decided by different officers. Someone sits down and evaluates your application and decides that this person gets 1,000 limit, this person gets 5,000 limit, and whatnot. All we are trying to do in this particular example is to replicate what they are doing. Okay? So we don't want the credit officer to do that. The credit officers sometimes are inconsistent from one another. They may have a good day or bad day. So we'd like to figure out what pattern do they collectively have in deciding the credit and have an automated system decide that. That's what the linear regression system will do for us. Okay, so the historical data here are, again, examples from previous customers. And the previous customers, this is X1 and this is Y1. So this is the application that the customer gave. And this is the credit line that was given to them, okay? No tracking of credit behavior. We're just trying to replicate what the experts do in this case. Okay, and then you realize that each of these Ys is actually a real number, which is the credit line that is given to customer Xn, okay? And that real number will likely be a positive integer. It's a credit line. It's a dollar amount. Okay, and what we are doing is trying to replicate that. That's the statement of the problem, okay? So what does linear regression do? First, we have to measure the error. We didn't talk about that in the case of classification because it was so simple. Here, it's a little bit less simple, and then we'll be able to discuss the error function for classification as well. What do we mean by that? Okay, you will have an algorithm that tries to find the optimal weights. Okay, these are the weights you are going to have. Okay, so these weights are going to determine what hypothesis you get. Some hypotheses will approximate F well, some hypotheses will not. We would like to quantify that to give a guidance to the algorithm in order to move from one hypothesis to another. So we will define an error measure, and the algorithm will try to minimize the error measure by moving from one hypothesis to the next. Okay? So if you take linear regression, the standard error function used there is the squared error. So let me write it down. Well, if you had a classification, there is only a simple agreement on a particular example. You either got it right or got it wrong. There is nothing else. Therefore, in that case, we just define binary error. Did you get it right or wrong? And we found the frequency of getting it right, and we got the E in and E out. Here, you are estimating a credit line. So if the guy gets 1,000 and you tell them 900, that's not too bad. If the guy gets 1,000 and you tell them 5,000, that's bad. So you need to measure how bad the situation is, and you define an error measure, and you define it by the simple squared error, okay? Now, squared error doesn't have an inherent merit here. It just happens to be the standard error function used with linear regression, and its merit really is the simplicity in the analytic solution that we are going to get. But when we discuss error measures in the next lecture, we will go back to the principle is, does error measure matter? How do we choose, etc. This will be answered in a principled way next time, okay? But for this time, let's take this as a standard error measure we are going to use. Okay, so when you look at the in-sample error, you use the error measure. So on the particular example, small n from 1 to capital N, for each example, this is the contribution of the error. Each of these is affected by the same W because H depends on W. So as you change W, this value will change for every example, and this is the error in that example. And if you want to get all the in-sample error, you simply take the average of those. Okay? So that will give me a snapshot of how my hypothesis is doing on the data set. And now we are going to ask our algorithm to take this error and minimize it. Okay? So let's actually just look at what happens as an illustration. This is the simplest case for linear regression. The input is one-dimensional. I have only one relevant variable. I want to relate your overall GPA to your earnings 10 years from now. Your overall GPA is X. Your earnings 10 years from now is Y. That's it. Okay? So I would have properly called this x1 according to our notation. And then there will be an x0, which is the constant one and whatnot. But I didn't bother because I have only one variable. Okay? But this is what we have. Okay, so you look at this and you see that, okay, for different x's, you have, these guys. Wow, your earnings are going down okay, well, I mean, that may not have been the example that is drawn here. Okay, so what linear regression does is tries to produce a line, which is what you have here, okay, that tries to fit this data according to the square error rule, okay? So it may look like this, okay? And in this case, the threshold here depends on W0. The slope depends on W1, okay, which is the weight for X. And that is what the solution you have. Now, you didn't get it right, but what you got is some errors. And you realize that, okay, so this is the error on the first example. This is the error on the second example. And if you sum up the squares of the length of these bars, that is what we call the in-sample error that we defined in the previous one, okay? Well, linear regression can apply to more than one dimension. And I can plot 2 dimensions here just to illustrate it. It's the same principle. What you have here is you have x1. Okay. If I can get the pointer. Okay, we'll leave it to rest. Okay, we have x1 and x2. And in this case, the linear thing is really a plane. Okay. And you are, again, not separating, but trying to estimate these guys, and you are making errors. And in general, when you go to higher dimensional space, the line, which is the reason why we call it linear, is not really a line. It's a hyperplane, okay? One dimension short of the space you are working with, okay? And that's what you are trying to use to approximate the guys. Okay. Now, let's look at the expression for En, and that is the analytic expression we are going to try to minimize, and that will make us derive the linear regression algorithm. Okay, so we wrote this before, and you have the value of the hypothesis minus yn squared. That is because it's a squared error, and because it's linear regression, this value h of xn happens to be w transpose xn. It's a linear function of xn, okay? Now, let us try to write this down in a vector form, okay? I will explain this in detail, but let's look at this. So instead of the summation, all of a sudden, I have a norm squared of something that is capital X. I haven't seen capital X before. I haven't seen vector Y before, okay? Well, it's basically a consolidation of the different xn's here. Xn is a vector. So you put the vectors in a matrix, you call it X. And you put the scalars, the yn, in a vector, and you call it y. So the definition of capital X and the vector y is as follows. Okay. For the matrix X, what you do, you put your first example here. Okay. So this would be the constant coordinate 1, the first coordinate, second coordinate, up to the dth coordinate, the last coordinate. Okay. And then you go for the second example and do the same and construct this matrix. And for y, you put the corresponding output. This is the output for the first example, output for the second example, output for the last example. Now, one thing to realize about the matrix capital X is that it's pretty tall. The typical situation is that you have few parameters. We reduce them to 3, for example, in the case of the classification of the digits. But you usually have many, many examples in the thousands. So this will be a very, very long matrix. Now, the way you take this, well, the norm squared will be simply this vector transpose times itself. And when you do it, you realize that what you are doing is summing up contributions from the different components. And each component happens to be exactly what you are having here. So this becomes a shorthand for writing this expression. OK. Now let's look at minimizing En. Okay. When you look at minimizing, you realize that the matrix X, which has the inputs of the data, and Y, which has the outputs of the data, are, as far as we are concerned, constants. This is the data set someone gave me. The parameter I'm actually playing with in order to get a good hypothesis is W. So En is of W, and W appears here, and the rest are constants. If I do any calculus of minimization, it is with respect to W. Okay? So I try to minimize this. And what you do, you get the derivative and equate it with 0. Except here, it's a glorified derivative. You get the gradient, which is the derivative on a bunch of them all at once. And there is a formula for it, which is pretty simple in this case. I will explain it. By the way, if you hate this and you want to sort of make sure, because linear regression is so important, and you want to verify that it's true, you can always go for the scalar form, get partial E by partial every W, partial W0, partial W1, partial WD, get a formula that is a pretty hairy one, and then try to reduce it, and surprise, surprise, you will get the solution here that we have in matrix form in 2 steps. Okay. Now, if you look at this, deal with it in terms of calculus as if it was just a simple square. If this was a simple square and my W was the variable, what would the derivative be? Okay, you will get 2 sitting outside. Well, you got it here. And then you will get the same thing in a linear form. You got it here. And then you will get whatever constant was multiplied by W to sit outside, which you got it here. You just got here with a transpose, because this is really not a square. This is the transpose of this times itself. That's where you get the transpose. Okay? Pretty straightforward and standard matrix calculus. So that's what you have. And then you equate this to 0, but it's a fat 0. It's a vector of zeros. You want all the derivatives to be 0 all at once. Okay? And that will define a point where this achieves a minimum. Okay. Now, you would suspect that the solution will be simple, because this is a very simple quadratic form. And indeed, the solution is simple. And if you look at it, you realize that, okay, if I want this to be 0, then okay, I want this to cancel out. So I want, when I multiply X transpose XW, I get the same thing as X transpose Y. So they cancel out, and I get my 0. So you write this down, and you find that this is the situation. I want this term to be equal to this term, and that will give me the 0. The interesting thing is that in spite of the fact that capital X, the matrix X, is a very tall matrix, definitely not square, hence not invertible, X transpose X is actually a square matrix, because X transpose is this way and X is this way. You multiply them and you get a pretty small square matrix, and as we will see, the chances are overwhelming that it will be invertible. So you can actually solve this very simply by inverting this. You multiply by the inverse in this direction and multiply by this. This will disappear, and you will get an explicit formula for W, which you are trying to solve for. And when you do that, you will get W equals this funny symbol, X dagger. Okay, what is X dagger? Okay, this is simply a shorthand for writing this. So I got the inverse of that, and then multiplied it by here. So this is really what I get to be multiplied by Y. I call it X dagger, and indeed it gets multiplied by Y to give me my W. Okay? Now, the X dagger is a pretty interesting notion. It's called the pseudo-inverse of X. X, being a non-invertible matrix, does not have an inverse. But it does have a pseudo-inverse. And the pseudo-inverse has interesting properties. For example, if you take this, the X dagger, and multiply it by X, so X dagger times X, what do you get? So you add X here, so you get X transpose X. Ooh, I have X transpose X minus 1 here. So they cancel out, and I get an identity. So when I multiply X dagger by X, I get the identity. So it's okay to call it an inverse of sorts, okay? It doesn't work the other way around. The other way around gives us an interesting matrix, which we'll talk about later, okay? But basically, this is the essence of it. If we were in a trivial situation where X was a square, I have 3 parameters, and I have 3 examples to determine them. That can be solved perfectly. I can actually get this to be 0. And how would you get it to be 0? You would just multiply by the proper inverse of X in this case, and you will get X inverse Y. So this is pretty much similar when X is a tall one, and we are not going to get a 0. We're just going to get a minimum using the pseudo-inverse. Now, I would like you to appreciate what the pseudo-inverse is from a computational point of view. Okay, so this is the formula for the pseudo-inverse that you will need to compute in order to get the solution for linear regression. So let's look at it, okay? Something is inverted, okay? And when you see inversion in matrix, you say, oh, computation. If this was, a million by a million, I'm in trouble. If this is like, 5 by 5, I'm in good shape. So we'd like to know what kind of matrix do we have here. Okay, well, nothing mysterious about what's inside this. You have this fellow, which is X transpose, okay? It's small d plus 1. D is the length of your input. 1 is the added constant variable. So these are the number of parameters. This would be 3 in the digit classification guy. We have only x1 and x2, so d equals 2. D plus 1 equals 3, which corresponds to x0, x1, x2, or to w0, w1, w2. Okay? So this is 3 times capital N. Capital N is the scary one. That's the number of examples. That could be in the thousands. Okay? Now, when you multiply this by x, and that's what you have. Okay, so the multiplication will be, okay, multiplication is not that difficult. Okay, even if this is 10,000, I can multiply this by 10,000. Okay, but the good news is that when I go to this guy, I will have to be dealing with a simpler guy. Let's just complete the formula first. This is what you have. This is what you are computationally doing. Okay, and if you look at what's inside here, it completely shrinks. That is what the matrix inside is. It's just 3 by 3 in our case. You can invert that. Just accumulating it is the one that you have to sort of go through all of the examples, and there is a very simple way of doing it. So it's not that difficult to get this fellow, okay? And you can see now that, oh, good thing that we had 3 parameters. If we had the 257 parameters to begin with, this would have been 257 by 257. Not that this will discourage us, but if you go for some raw inputs, you can get something really in the thousands or sometimes even more than that. Okay, so the computation aspect of this is very simple, and there are so many packages for computing the pseudo-inverse or outright getting the solution for linear regression that you will never have to do that yourself, except if you're doing something very specialized. If you do have something to do something very specialized, it's not that bad. Okay. So that is the final matrix, and the final matrix will have the same dimension as this guy. Okay. And if you look at it, this will be multiplied by what? Multiplied by y, which is y1, y2, y3, yn, corresponding to different outputs. And then, as a result of that, you will get the w's, w0, w1, up to wd. Indeed, if you multiply this by a n tall vector, you will get a d plus 1 tall vector, and that's what we expect. Okay. So let's now flash the full linear regression algorithm here. Okay, that's a crowded slide. Okay. That is what you do. The first thing is you take the data that is given to you and put them in the proper form. What is the proper form? You construct the matrix X and the vector Y. And these are what we introduced before. This will be the input data matrix, and this would be the target vector. Okay? And once you construct them, you are basically done. Because all you are going to do, you plug this into a formula, which is the pseudo-inverse, and then you will return the value W that is the multiplication of that pseudo-inverse with Y. And you are done, okay? Now, you can call this one-step learning if you want, okay? With the perceptron learning algorithm, it looked more like learning because I have an initial hypothesis, and then I take one example at a time and try to figure out what is going on, move this around, etc. And after 1,000 iterations, I get something. It looks like more than what we learn. We learn in steps. This looks like cheating. You give me the thing, and whoop, and you have the answer, okay? Well, as far as we are concerned, we don't care how you got it. If it's correct and gives you a correct E out, you have learned, okay? And because this is so simple, this is a very popular algorithm that is used often and used often as a building block for other guys. We can afford to use it as a building block because the step here will be so simple that we can become more sophisticated in using it. Just one remark about the inversion. This has to be inverted in order for this formula to hold. Now, the chances are that this will be invertible in a real application you have is close to 1. Okay? The reason is the following. Usually you use very few parameters and tons of examples. Okay? You will be very, very, very unlucky, okay, to have these so dependent on each other that you cannot even capture the dimensionality, which is the number of columns. The number of columns is 3, 5, 10, and you have 10,000 of those. So the chances are overwhelming in a real problem that this will be invertible. Nonetheless, if it is not invertible, you can still define the pseudo-inverse. It will not going to be unique and has some elaborate features, but it's not a big deal. That is not a situation you will encounter in practice. Okay. So now we have linear regression. So I'm going to tell you that you can use linear regression not only for real valued function, for regression problems, but you are also going to be able to use it for classification. Okay? Maybe the perceptron is now going out of business. It has a competitor now, okay? And the competitor has a very simple algorithm, okay? So let's see how this works. The idea is incredibly simple. Linear regression learns a real valued function. Yeah, we know that. Okay, that is the real valued function. The value belongs to the real numbers. Fine. Now, the main observation, the ingenious observation, is that binary valued functions, which are the classification functions, are also real valued. +1 and -1, among other things, happen to be real numbers. So linear regression is not going to refuse to learn them as real numbers, right? So what do we do? Okay. You use linear regression in order to get a solution such that the solution is approximately yn in the mean square sense. So for every example, the actual value of the signal is close to the numerical +1 and the numerical -1. That's what linear regression does. Okay? Now, having done that, with yn equals + or -1, you realize that in this case that if you take the classification version of it, you take the sign of that signal in order to be able to classify as +1 or -1, if the value is genuinely close to +1 or -1 numerically, then the chances are when it's +1, this would be positive, and when it's -1, it's negative. The chances are you're getting close to a number, you'll probably cross the 0 in doing that, okay? And if you cross the 0, the classification will be correct. So if you take this and then plug it in as weights for classification, you will likely get something that will give you likely to agree with + or -1, okay? That's a pretty simple trick because it's almost free. All you need to do is have a classification problem. Let's run linear regression. It's almost for free. Do this one-step learning, get a solution, and use it for classification. Okay, now let's see if this is as good as it sounds. Well, the weights are good for classification, so to speak, just by conjecture, but they also may serve as a good initial weights for classification. Remember that the perceptron algorithm or the pocket algorithms are really very slow to get there. You start with a random guy, half the guys are misclassified, and it just goes around, tries to correct one, messes up the others, until it gets to the region of interest, and then it converges. Why not give it a jump start? Why not run linear regression first, get the W's? We know that the W's are okay, but they are not really tailored to our classification, but they are good initial condition. Feed those to the pocket algorithm and let it run to the solution, which is a classification solution. Okay? That's a pretty nice idea. So let's actually look at the linear regression boundary. Okay. Now, I take an example here. Again, I have the +1 class and the -1 class, and I applied trying to find what is the linear regression solution. Now, you remember the blue region and the pink region belong to classification. Okay? When you talk about linear regression, you have the value here, and the signal is 0 here. The signal is positive, more positive, more positive, more positive, and here the signal is negative, more negative, more negative, more negative. There is a real valued function that we are trying to interpret as a classification by taking the sign. Now, if you look at what the linear regression is trying to do when you use it for classification, all of these guys have a target value -1. It is actually trying to make the numerical value equal -1 to all of them. So the chances are these will be -1. This will be -2, -3, and the linear regression algorithm is very sad about that. It considers it an error, in spite of the fact that when we plug it into the classification, it just has the correct sign, and that's all we care about. But we are applying linear regression. It is actually trying very hard to make all of them -1 at the same time, which obviously it cannot. And you can see now the problem with linear regression. If in its attempt to make this -8 -1, it may move the boundary to the level where it's in the middle of the red region, and now it's very happy because it minimized its error function, but that's not really the classification. Nonetheless, it's a good starting point, and then you take the classification now that forgets about the values and try to adjust it according to the classification, and you will get a good boundary. That's the contrast between applying linear classification, linear regression for classification, and linear classification outright. Okay.